Hi everyone, thank you so much for clicking onto the video. Today's learning objective is to be able to deduce the empirical, molecular and structural formulae of compounds from data obtained from combustion analysis, elemental percentage composition, characteristic reactions of functional groups, infrared spectra, mass spectra and nuclear magnetic resonance. So now we're going to go on to finding the empirical and molecular formulae. So we need to know how to work out both of these formulae from data giving composition by mass or percentage by mass. So we have a general method. And the first step is to divide the percentage by masses or the composition by masses, depending on what you get in the question, of all the elements by their corresponding relative atomic masses. And this is basically to find how many moles we have of everything. And then we divide all the values by the smallest value. And this is basically giving us the simplest whole number ratio. So then we use this ratio to find the empirical formula. And if we want to find the molecular formula, apply every element in the empirical formula by this unit to find the molecular formula. So in this example, a compound contains 40 grams of carbon, 6.7 grams of hydrogen, and 53.5 grams of oxygen, and it has a relative molecular mass of 60. So then we're told to find the empirical and molecular formulae of this compound. So the first thing I like to do is to write out all of the atoms we have, so all of the elements. So we have carbon, and then hydrogen, and I always find it quite useful to space them out. So the next thing I do is write out everything that I've got. So I've got 40 grams of carbon. And then, so the first step is to divide by the AR of every single element. So that's our first step. So we have 40.0 over the AR of carbon, which is 12.0. And so this gives us 3.33. And then we have 6.7 over the AR of hydrogen, which is 1.0. And so this gives us 6.7. And then we have 53.5 divided by the AR of oxygen, which is 16.0. And that gives us 3.34. And the next step we have is to divide by the smallest. So the smallest we have is 3.33. So we divide everything by 3.33. So we have 3.33 divided by 3.33, and that equals 1. And then we have 6.7 over, and then we have 3.34 over 3.33, and this gives us 1.00. So it's always a good idea not to round these very much, because sometimes if it's 1.5, that is actually what we take it as. So when we try and find the empirical being 1 or 2. And then the next step is to find the empirical formula. So first what we do is find the ratio. So the ratio we have is 1 to 2 to 1, because this 2.01 is very, very close to 2. And so that's what we take it as. And so we have that the empirical formula we then find the units, the unit of the empirical formula, and then multiply this empirical formula by the unit. So the molecular formula they've given us, the molecular mass, is 60. So that's the MR of the compound. So we've got the equation that the unit of the empirical formula is equal to the MR divided by the MR of the empirical formula. 2, and so therefore the molecular formula multiplied by 2. So we have C2H4 and then O2. Now we're going to look at combustion analysis. So we can find the percentage composition of a compound using combustion analysis. And so what we have is a known mass of a compound which is burned in an excess of dry oxygen, and we also have the masses of carbon dioxide produced and water produced. And for a compound containing only carbon, hydrogen and oxygen, we can work out three things. We can work out the percentage of carbon from the mass of carbon dioxide produced, and then we can work out the percentage of hydrogen using the mass of water produced, and then finally we can work out the percentage of oxygen using A and B, because we can do 100 minus the percentage of carbon and the percentage of hydrogen. So in this example, we're going to look at if 3 grams of a compound containing only carbon, hydrogen and oxygen was burned and produced 8.20 grams of carbon dioxide and 3.50 grams of water, calculate the percentage composition of the compound. So what we do first is let's work out the mass of carbon that we have. So the mass of carbon, which is in 8.20 grams, is equal to, if we think about how much carbon we have in carbon dioxide, so carbon is C and carbon dioxide is CO2. So if we put the AR of carbon over the MR of CO2, then we should be able to get a fraction. So the AR of carbon is 12, and then the MR of carbon dioxide is 12 plus 2 times 16. So this gives us how much carbon is in 1 mole of carbon dioxide. And then we times this by the 8.20 because that's the mass of carbon dioxide that we produced. And so this gives us 2.24 grams. And now we can work out the percentage of carbon in the compound by doing 2.24 over the whole mass of the compound, which is 3, and then multiplied by 100. So this gives us 74.7%. And then we can work out the mass of hydrogen. So we have that the mass of hydrogen in 3.50 grams of water produced. So it's best to put that as well. Carbon dioxide produced, and this one's of water produced. So we do the same thing. So we think about hydrogen and then also water. So we put the AR of hydrogen on the top. So we have 1.0. And then the MR of water is 2 times 1.0. And then added with 16 for the oxygen. So this gives us the fraction of how much hydrogen we have in a water molecule. And then, of course, we need to multiply it by the 3.50 grams of water produced. And so this gives us 0.39 grams. And then again, we can work out the percentage of hydrogen in the compound. So we have the percentage of hydrogen in this compound is equal to 0.39, again, over the total mass of the compound, which is 3, and then multiplied by 100. And this gives us 13.0%. So now we can work out a percentage of oxygen, because this compound only contains carbon, hydrogen and oxygen, and we already know the percentages of carbon and hydrogen. So we have that the percentage of oxygen in the compound, which is equal to 100%, minus the percentage of carbon we have, which is 74.7, and then minus the percentage of hydrogen we have, which is 13.0, 12.3%. So we have that the percentage of carbon in the compound is 74.7, and then we have 13% of hydrogen in the compound, and 12.3% of the compound is oxygen. We also need to know all the characteristic reactions of functional groups. So here's a quick summary table. Firstly, we have alkenes, which have this carbon-carbon double bond, and how we test for this double bond, or what we call unsaturation, is we add bromine water. And what happens is that the orange colour will turn colourless, so the bromine will decolorize. And a note is that carbonyls, so aldehydes or ketones, will decolorize bromine water very slowly. However, phenols, which are benzenes with an OH group, will decolorize it and also produces a white precipitate. And then looking at haloalkanes, the general formula we have is an R group, so an alkyl group, and then an X. So the X will be a chlorine, a bromine, or an iodine. So fluorine isn't counted. And what we do to test for haloalkanes is we warm it with some sodium hydroxide, which is aqueous, and then add some dilute nitric acid, and then we add a few drops of silver nitrate. So we add the acid to get rid of any carbonates, which could also produce a precipitate. So chloroalkanes will produce a white precipitate, bromoalkanes will produce a cream precipitate, and iodoalkanes will produce a yellow precipitate. And how you remember that is that going down the group, the precipitate gets more and more yellow. So first you start off with white, and then cream, and then yellow. And a note is that the chloroalkane and bromoalkane precipitates are both insoluble in dilute ammonia, whereas the bromoalkane precipitate is soluble in concentrated ammonia, and the iodoalkane precipitate is insoluble in both dilute and concentrated ammonia. Then looking at hydroxy groups, which are just OH groups attached to different compounds, what we do is add solid PCl5, and we should see some misty fumes if there are hydroxy groups present. And both alcohols and carboxylic acids will produce misty fumes, but phenols won't. And then for primary alcohols, these can be oxidized. So what we do is we add acidified potassium dichromate solution, which is an oxidizing agent, and it turns from orange to green because the dichromate ions are being reduced to Cr3 plus ions, which are green. And the organic product will produce a silver mirror with Holland's reagent. And this is because the organic product produced is an aldehyde, and that can be oxidized further because Holland's reagent is another oxidizing agent. And then for secondary alcohols, we again add acidified potassium dichromate solution and warm. And so again, the solution turns from orange to green. And this time, the organic product doesn't produce a silver mirror with Holland's reagent. And this is because secondary alcohols are oxidized to ketones, but ketones can't be oxidized any further. And so we won't get this silver mirror. Then for carbonyls, what we do is add 2,4-dinitrophenylhydrazine, and an orange precipitate should form. And both aldehydes and ketones will produce an orange precipitate. Then for aldehydes, we add Holland's reagent and warm it, and so we should get this silver mirror. And we can also use Fehling's or Benedict solutions, and ketones will not react with any of these three solutions because they're all oxidizing agents, and ketones can't be oxidized any further. And then to identify a CH3C double bond O group in carbonyls or a CH3CHOH in an alcohol, what we do is add an alkaline solution of iodine and warm it, and a yellow precipitate should form. And this is what we call the triiodomethane or the iodoform test. Then for carboxylic acids, we add either sodium hydrogen carbonate or sodium carbonate and warm if necessary, and we should get some effervescence. So we should get some bubbles of gas forming because we should form carbon dioxide gas. And then finally for phenols, what we do is add some bromine water, and the bromine will immediately decolorize and we should form a white precipitate. And one thing to note is that phenylamine, so a benzene with an NH2 group, will produce the same result. But the way we can distinguish between a phenol and a phenylamine is that the phenol will be soluble in sodium hydroxide but insoluble in dilute hydrochloric acid, whereas phenylamine is insoluble in sodium hydroxide but soluble in dilute hydrochloric acid. Now we're going to look at combining all the techniques that we've learnt. So we can use a combination of techniques to identify organic compounds and determine their structures, including mass spectrometry, which allows us to determine the accurate relative molecular mass of a compound, and also the fragmentation patterns, which can suggest possible groups present. We can also use infrared spectroscopy, which allows us to identify particular functional groups which are present in an organic compound, and then also NMR spectroscopy, so carbon-13 NMR, which allows us to identify the number of different environments for carbon atoms in a compound. And then we also have hydrogen-1 or proton NMR, which allows us to identify groups of hydrogen atoms in a compound. And another thing with the proton NMR is that we also get splitting patterns. And these allow us to identify the number of hydrogen atoms on an adjacent carbon atom. So in this example, a compound is made of 62.07% of carbon, 10.34% of hydrogen, and 27.59% of oxygen by mass, and it produces an orange precipitate with 2,4-dinitrophenylhydrazine, but doesn't react with Fehling's or Tollens. And the proton NMR spectrum of the compound has a single peak with a chemical shift of 2.2 parts per million. The peak area corresponds to 6 hydrogen atoms, and its mass spectrum and infrared spectrum are shown below. Use all of the given information to determine the structure of the compound. So firstly, we're going to look at the empirical formula because that's probably the easiest thing to do first. And we can find out its empirical formula by using its composition by mass. So we do it exactly in the same way as we would normally. So we set it out as carbon and then hydrogen, and then we also have oxygen. So carbon is 62.07%. Then hydrogen is 10.34%. And then we have 27.59% of the oxygen. So first thing we do is divide by all of the relative atomic masses. So we have 62.07 over 12.0, and this gives us 5.17. And then we have 10.34 divided by 1.0, which is equal to 10.34. Then for oxygen, we have 27.59 divided by 16.0, and this gives us 1.72. And then we divide by the smallest. So the smallest is the 1.72. So we have 5.17 divided by 1.72, and this is equal to 3.01, and then we have 10.34 divided by 1.72, which is equal to 6.01, and then finally we have 1.72 divided by 1.72, which is equal to 1.00. And so here we've divided by the smallest. And so now we have our ratio for this compound of the different elements in this compound. So we have that the ratio is equal to 3 to 6. And so our empirical formula is equal to C3H6O. And now we have to try and work out our molecular formula to actually see how many of each element we actually have in this compound, because the empirical formula is just the simplest whole number ratio. So how we do that is we look at our mass spectrum. So this one on our left is our mass spectrum. So this is what we get from our time of flight mass spectrometer. And because this is a simple molecule, we look at the highest peak, which has the highest MZ ratio. So the peak with the highest MZ ratio would be this one. However, this isn't the largest peak, and so it's not this one. So we're actually looking for this one here. And this is at an MZ value of 58. And this is what we call the molecular ion peak. And because this molecular ion peak is at an MZ value of 58, this is actually the relative molecular mass of this compound. So we have the relative molecular mass is 58. So from the mass spectrum, we have that the relative molecular mass, or the MR, is equal to 58. And so the way we work out our molecular formula is to first work out the unit of the empirical formula, and then we have to multiply everything in this empirical formula by this unit. So firstly, looking at the MR of the empirical formula. So we have 12 times 3, and then we add 6 times 1, and then we also have a 16.0. And this actually gives us 58.0. And so our empirical formula is actually our molecular formula. Because our unit of empirical formula would actually just be equal to 1. And now we can look at the other information that we have. So also in the question, it said that it produced an orange precipitate with this 2,4-dinitrophenyl hydrogen. And we know that when we react 2,4-dinitrophenyl hydrogen with an aldehyde or a ketone, so a carbonyl group, it should produce an orange precipitate. And so this tells us that we've got a carbonyl group. So we could just annotate this question. So we have a carbonyl here. And then the next bit says that it does not react with phthalings or toluenes. And so we can write this down. So we can write down that because this 2,4-dinitrophenyl hydrogen an orange precipitate when reacting with this compound, we know that it has to be either a ketone or an aldehyde, because it has to be a carbonyl compound. It has to have the C double bond O. So we've got 2,4-dinitrohydrogen forms an orange precipitate. And so this means we have to have a carbonyl. And then what we have is that it doesn't react with toluenes or phthalings. And so this tells us that we must have a ketone, because aldehydes can be oxidized further. So now we can look at our other spectrum that we have, which is this infrared spectrum. And we can see that we have a peak here, this peak, at about 1,720 centimeters to the minus 1. And looking at our data booklet, this actually corresponds to a C double bond O group. And so this is our idea of it being a carbonyl compound. So again, we have to write that down. So we have an absorption at 1,720 centimeters to the minus 1. So this indicates to us that we have a C double bond O, so a carbonyl. So this confirms that we could have a ketone or an aldehyde, but of course we can only get a ketone because we don't have a reaction with Toluene's reagent or phthalate solution. And then finally, looking at the information we have about the proton NMR. So the question said that the proton NMR spectrum of the compound has a single peak with a chemical shift of 2.2 ppm, and also the peak area corresponds to 6 hydrogen atoms. And so because it's a single peak, we know that all of the hydrogens, all of these 6 hydrogens, are in the same environment because they only produce one peak, and they have a chemical shift of 2.2 parts per million, which, if we look at our data booklet, corresponds to hydrogen attached to a carbon, which is then attached double bonded with an oxygen. So what we have from this proton NMR, we have that at 2.2, and what this suggests is that we have a hydrogen attached to a carbon, and then this carbon is then attached to another carbon double bonded to an oxygen. And also we have a single peak area of 6 hydrogens. And so what this tells us is that all 6 hydrogens are in the same environment. And so the only way we can get 6 hydrogens in the same environment is if we have 2 methyl groups. So if we have CH3, CH3. And so now we can use our molecular formula and what we've learned from this proton NMR, and also that it's a ketone, to work out our structure. And because we have 2 CH3 groups from this proton NMR, that means that these 2 are then attached to the 3rd carbon. So what we have is CH3, and then because we can't attach a double bond oxygen to either of these carbons, that means that the carbon which they're both attached to has to have the double bond oxygen. And so it must be this carbon which has this double bond. And so our compound is actually propanone. And we can actually check this because it will form an orange precipitate with 2,4-dinitrohydrazine because it's got this carbonyl group, the C double bond O. It won't react with toluenes or phthalenes because it's a ketone, so it can't be oxidized further. It does have an infrared absorption at 1,720 centimeters to -1 because of this carbonyl group. And also, we do have a hydrogen, so for example, this one here, which is attached to a carbon, which is then attached to a carbon with this double bond oxygen. So we also have this peak at 2.2 parts per million. And then finally, we do have a single peak with an area of 6 hydrogens because these 3 hydrogens are in the same environment as these 3 hydrogens. So we have 6 hydrogens in the same environment and producing a single peak because there's no hydrogens on this carbon here.